Okay, Ji. So now we're going to discuss. In the previous lecture, we discussed the different configurations of different important pieces of hardware with respect to your LANs, and how, in fact, both LANs, both we started discussing the different pieces of hardware that are important to your coaxial LANs, and we looked at the different pieces of hardware that came into importance with respect to your Ethernet LANs, and then we studied the wireless LANs as well. So this was what happened in the previous lectures. Now we're going to move on and study the basic Ethernet protocol, how it has evolved over the years, and why Ethernet, studying Ethernet is important, because we are right now discussing the working of the local area network, and that's why it should be important to understand the protocol that is being used for Ethernet networks. Okay, so now Ethernet network is a prevalent technology in modern network world that is primarily focused on the local area networks. Originally introduced in the 1970s, was later taken up by the 802 committee of the IEEE Institute of Electrical and Electronics Engineers for further development. The Ethernet standard, which is also known as the 802 IEEE 802.3, has been since evolved into 5 generations. So basically, 802 is the committee number of this Institute of Electrical and Electronic Engineers, and originally it started off with a very basic data transfer bitrate, but overall it has evolved into different generations. So it started off with the standard, then it moves off to fast, then gigabit, 10 gigabit, and 100 gigabits. So basically, this title of gigabits refers to how many bits per second it can transfer. So basically, as you can see here, current standard is allowing 100 gigabits per second data transfer rate. So that's pretty high. The original, by term original, is also referred to as the legacy systems. So the original or legacy Ethernet configurations were either bus topology or star topology with a hub or as a central device. Now, as you remember that we in the previous lectures we have discussed how a star topology is implemented, and basic configuration of a star topology is that we've got the central device and all other communicating devices are connected to the central device. Now, this central device basically is linked with a direct connection from the central device to each and every terminal. And this central device allows the communication between all other communicating servers. For example, this is my bus, this is my star topology, and this is the central device right here. As you can see here, all connected terminals are linked with the central device with a dedicated channel. Now, this dedicated channel is only used for this terminal only. So I don't have to wait for this channel to be free. I can start communicating whenever I want to. So there is no multiple access as we saw in the bus topology. There is only with there is a dedicated channel. Now, but this central device is if it's a hub, then that means that hub will actually be behaving like a bus topology. So that's what the line meant. Okay, it behaves like a bus topology. Now, by that, let me explain here that if it's a star topology with a hub, that means each transmission with a hub, by the way, is broadcasted. So if, for example, I'm using a hub as the central device over here, and this computer, for example, wants to transfer data to this computer, what that hub does is that it transfers it to all connected computers. So this is essentially the working of how a system is broadcasted. This is one sender, and everyone who is connected to the network is the intended recipient. Even though it's not intended, intended is wrong word, but they end up being the recipients. The intended recipient is only this computer right here. So again, with your regular bus topology where information is being broadcasted, every other unintended computer that is receiving the transmission will verify whether or not it was intended for this transmission by looking at the intended recipient's MAC address. So if its MAC address was if the MAC address mentioned in the incoming transmission is its own, then that means that this transmission is meant for this computer. Otherwise, it would proceed in deleting the transmission, and only the computer that was supposed to receive the transmission, whose MAC address is mentioned in the incoming transmission, will further, forward the data for further processing. So basically, what that means is that if I'm using a regular bus topology, or even if I was using a star topology, earlier configurations of Ethernet implementations were either bus, or they use star topology with a central hub. In either case, data transmissions from one device to another are only going to be broadcasted. Now, since each end system would receive all messages, every end system would have to check the destination address for incoming message, and the address they are looking at is the MAC address. That is the address that is linked to each connecting network interface card. In the previous lecture, we also discussed the network interface card, and that is the device that allows network connectivity of any kind to all devices that are capable of connecting to a network. So if it's a regular Ethernet network, then you will see that your computer will have an allowed Ethernet port on it. So that is a network interface card that has an Ethernet port on it. Earlier representations of such a network would allow for a BNC connector. For BNC connector, that meant that that is a coaxial cable connecting to it. But newer technology, they have shifted towards a wireless setup. So that means now network interface cards are actually wireless network interface cards, and that means that those computers are capable of connecting to wireless access points that allow access to a network on its own. So in either case, when data transfer is being carried out and is being broadcasted, all unintended computers receive messages as well, but they deny those, they ignore those messages based on the recipient's MAC address. Since it's not theirs, they're not bothered about any further processing of that data. Only the computers that are intended recipients will further process it. Okay, now let's look at CSMA CD once more in a little more detail. Now, as you remember that we discussed CSMA CD in previous lectures when we were talking about the bus topology. And CSMA CD basically means carrier sense multiple access with collision detection. Now, collision or chances of collisions is actually a very prevalent problem in bus topologies. Why is that the case? Because as you remember, the bus topology is basically a sort of configuration, is a topology, is an arrangement for a network in which there is a common shared bus that is shared amongst all connected terminals. And this central bus, which is also known as the central backbone, the main backbone of the entire network, is the main means of communication between all connected terminals. So if this computer wants to send data to this, it will send it via this central bus. Now, since this central medium is shared, that means that other devices will also want to send data at some point, and they will have to actually wait their turn, because at one time only one data transmission could be carried out on the central bus. So this invites a lot of confusion with respect to what device will get chance first. So to avoid, and if for example this has is not established beforehand, before transmitting data, that they are in fact the only computers transmitting information, then there's a great chance that the data they transfer will actually collide with any other computer that is also transmitting at that time. And this collision is actually, in other words, is this collision means that there's a data loss. Information is being lost and nobody receives any information. This is loss of data, loss of time, loss of processing resources, and no information has reached their intended destination. So to avoid such a situation using bus topology, and you remember that there was a time that only bus topology was available for local area networks, and to cope with this issue of multiple access and chances of collision, a set of steps were established. A set of steps for all computers was made mandatory. This was known as carrier sense multiple access with collision detection. Now this technique was used to avoid any chances of collision, and if the collision did was occurring, there were steps to handle that as well, without or with minimal loss of any data of any kind. Now let's look at these steps in detail. Whenever a shared medium is used for data transfer, there is a possibility of messages to be corrupted during transmission. And that is what is the case for your bus topology. This especially happens when we have two end systems that transmit at the same time, creating what is known as a collision. Now, collision basically means that data is being lost. The data is, in a sense, colliding with each other and is being corrupted. And corrupted data means that it cannot be used for any further processing. It has no value of information whatsoever. Now, voltages of individual transmissions interfere with each other and thereby corrupting messages. So basically, in detail, when a collision occurs and when data is being transmitted, that means that every transmission has its own voltage, and individual voltage transmissions interfere with others, and thereby they start corrupting information. To deal with this, carrier sense multiple access with collision detection method has been adopted, which largely relies on generation of voltage level when the message was being transmitted on the Ethernet cable, and that can be detected. So essentially, I am looking forward towards that voltage rise. Why? Because that means some device is transmitting. So if I can detect that, that means before transmission, if I can detect that, that means that currently some other device is actually transmitting data, and therefore I should wait my turn. If I do not verify this beforehand and I simply proceed towards sending data without verifying this, that would mean that I transmitted data possibly at the same time as someone else was transmitting data, and this would lead to collision. The steps for such carrier sense multiple access with collision detection are as follows. Check the voltage on the transmission medium, and if it's risen, that means transmission is being carried out. If this indicates activity, wait for a random amount of time before checking again. Now, why does it mean random? What is importance of a random amount of time? Well, think about it this way. If you are sensing the medium, so this is basically what we did here is checking the voltage on transmission medium. That is actually the carrier sensing part. And carrier is the central bus, the central backbone cable in this bus topology that we are using for data transfer. That is the carrier in this case. And carrier sensing is basically, in simple terms, determining whether or not some other computer is also transferring data at the same time. That is carrier sensing. And how it's done is basically monitoring the voltage levels. If they are risen, that means the transmission is taking place and you are not supposed to transmit at that time. Now, if carrier sensing results in the rise of voltage, that means that right now I should not transmit and I should wait a random amount of time. Now, why we're talking about random amount of time? Why random amount of time? But think about this. You're not the only device who may want to transfer. It is possible that other connected devices may also want to transmit at that same time, and they may also have checked the central bus for voltage levels, and they too found them to be busy. So they also have to wait. Now, if you and all other devices who are intending to transmit wait for the same amount of time, that means they will again, at this the same amount of time, after that same amount of time has passed, all the concerned devices will start transmitting at the same time, because all of them will feel the carrier to be free at the same time, and all of them will simultaneously start transmitting. Because of this will result in collisions. So it is very important that every concerned device which intends to transmit data waits for a random amount of time, so that, say for example, two devices were intending to transmit, they both sensed the carrier and they found risen voltage levels, because of which they both backed off. They don't want to transmit now. They will wait, but they will wait a random time. Device A waits 5 seconds, device B waits 7 seconds. And neither device knows how many seconds each other device is waiting. Now let's just say, for example, seconds term is being used here, and device A waited 5, device B waited 7. Now after 5 seconds, device A will attempt to sense the carrier again, and if it found it free, it will start transmitting. And device B, after 7 seconds, will sense the carrier carrier, and if say device A is still transmitting, it will back off because now it's busy. However, say both A and B were both waiting for 5 seconds, and after 5 seconds, let's say both devices reattempted to sense the carrier and they both found it free. That means they will both start transmitting data, because of which this both simultaneous data transmission will result in collisions, because at one time only one device can be communicating, sending data transmission on that central bus. Okay, after that, if say they ran after a random amount of time, the possibility of a collision has reduced. So if after random amount of time a device detects that there is no activity, there is no risen voltage levels on the central cable, so that means the carrier is now free, and that device will now start transmitting data. And at the same time, it will continuously check for its transmission to see if a collision has occurred while transmission. Now, this is the aspect of collision detection. So, even while transmitting, each device is supposed to check on whether a collision has occurred. Now, the reason that is done is because let's just say that for some reason two devices did start communicating at the same time, and for some reason the random amount of time did, however, come out to be similar or whatever it is, and two simultaneous devices ended up simultaneously transmitting data at the same time. And this is double check, by the way. So let's just say, for example, the random amount of time turned out to be same, and because of that both devices started transmitting at the same time. It's very rare, but let's just say it did happen, because of which both devices, since they are transmitting at the same time, both of their transmissions will be lost. It will be collided because at one time only one device can communicate. So both of their transmissions are being collided. Now, how are they checking for their collisions as they are transmitting data? How are they checking for, continuously checking for collision? Well, it's quite simple. They are simply listening into their own transmissions, Now, as you remember, that bus topology allows for data to be broadcasted. So technically, you as a sender may also be receiving your transmission. So if you can listen into your transmission again and you see your own transmission in a corrupted, distorted manner, that means every other device will be also hearing the same way. That means your data is being collided, and which also means that some other transmission is also being carried out right now. So as soon as you detect a collision by this way, by listening into your own transmission, your job is to back off right then and there. And by backing off, you mean you stop your transmission instantly. Now, why is that important? Because if you keep on transmitting, that means you're doing this for no reason. You're transmitting data, nobody's going to listen, nobody's going to receive anything. All they're receiving is noise, distorted data. So why waste valuable time, valuable bandwidth, and for no reason? So you instantly back off. And then again, if a collision is detected, stop transmission of message and transmit a jamming signal to warn all end stations. And after a random amount of time, try again. And this is also important. Since you're receiving a collision, that means other devices who other were also were transmitting, because of which collision occurred in the first place. All other devices and your device as well will transmit a jamming signal, which will be interpreted by all devices, and all concerned devices who were simultaneously transmitting at that time, leading to a collision, will stop their transmission instantly. And after that, they will wait again a random amount of time, because they want to reduce the chances of a collision occurring again. They will wait a random amount of time. After that, they will start sensing the carrier again before they can start transmission. So this is basically what carrier sensing multiple access with collision detection does. Now, it does appear to be a very complicated procedure. Yes, it is. And to be honest, this was what they had to work with at that time, when bus topology was the best approach towards a local area network. And bus topology, regardless of its setbacks, bus topology is in fact a very simple and robust network. And for its time, it was a very good approach to a local area network. And its setbacks include chances of collision, and we handle collision this way. Now, when the star topology became popular, that's when your, and especially when in the event of a switch, your star configuration with the switch was implemented in such a way that you really didn't need a carrier sensing multiple axis collision detection anymore. Well, and why? Primarily because there is no shared medium anymore. You have, each computer has its own dedicated channel. There is no shared medium. Therefore, you don't require any carrier sensing because this channel is there for you, only you. So whenever you want, whenever this computer wants, it will start transmitting. It doesn't have to wait for the channel to be free. It's free just for him, for this computer right here. So there is no need for carrier sensing because there is no multiple access. This channel is only reserved for this computer. However, will a collision occur? Of course not, because there is only one transmission carried out in this channel and there's no chances of a collision. So that's when we started shifting towards a LAN with a switch using star configuration. The switch as the central device, each system is connected to the central device via full duplex connection, which both directions that are transmitted can be carried out simultaneously. Since the link is dedicated, there are no chances of collision, and that's why carrier sense multiple access with collision detection was not needed anymore when we moved towards the SAR configuration, which is most commonly used now, and particularly when the central device was a switch. So considering these two features, CSMA CD was not needed anymore. It was needed till the bus topology was still being used and data was being broadcasted and medium was shared. However, there might be a high levels of activity at the switch, and the switch needs to be able to store incoming messages in a buffer until the cables are free for transmission to take place. Now, this is very interesting. This is one of the problems that possibly switches will or star topology will face. Now, this is only one device, and this central device is responsible for relaying all outgoing messages to their intended recipients. So for example, if every device is, by the way, capable of both sending and receiving data, we have full duplex communication at the same time. So that means every device may be sending device data to some other device. But we only have one device here. The central device is only one. And there are many connected devices that this central device has to cater to. So that means the process, the speed at which the central device is forwarding data may not be at the same speed as it's receiving data. So it may be receiving requests for data transfer much more faster than it's actually forwarding the message. So that delay in receiving message and then forwarding it to intended recipient will cause the data to be starting piling up in the central device. Now, this central pileup of data, if not handled properly, will result in data loss, information loss, and that should be avoided. Now, to deal with that, we are maintaining a central buffer inside this device, a buffer inside of this device. Now, as with always, buffer is a temporary storage device that is used for catering the speed differences of two connected devices. Now, in this case, it's not just two connected devices, many devices, but yes, we are still catering speed difference. In which case, the speed difference in concern here is the speed at which this central device is receiving messages and the speed at which it is sending messages out. The speed of sending messages out, and especially considering the fact that not all mediums may be free at the same time, and sending data to them may not always be possible, and we will have to wait for some time. Considering all these factors, this central device is not capable of sending messages out as fast as it's receiving messages. Now, if I don't maintain a buffer here, that means those messages that I was not able to forward on time will be lost, and that results in information loss. So to avoid that, a central buffer, a buffer on your message buffer on your central device is maintained, and it's kept, data is kept there until data transmission is possible, and this results in no data loss whatsoever. Now, in the next lectures onwards, we'll be looking at how the infrastructure of the internet starts growing. So far, we were focusing on LANs and their configuration, how they've evolved over time, what types of hardware they use, and how they are configured to connect with other devices, how they have evolved to the most modern approach, which is the switch right now with star configuration with the central switch at the end. So this is the most, modern approach, this most perfect approach right now. It has minimum problems, and we have upped its speed by using fiber optic variants as well, but essentially the basic configuration is switched right now. And we saw how different techniques were used in the past to manage the optimal data transfer in other varieties of local area networks. But now let's move towards the wide area network, particularly the internet. And when we're calling the internet is just another wide area network. In fact, it is the largest ever wide area network. And if you go back to the definition of the wide area network, it's basically a network of networks. If you remember the banking example that we quoted in class, basically a banking system for an entire country involves a lot of branches, and all of these branches are working together. You can be a bank account holder in a branch in Lahore and access your branch from anywhere around Pakistan, because that bank is part of a wide area network that is accessible all over the country. And thing is that you are accessing an account from a branch, and one branch is a local area network. So any user of that network, may it be an account holder or a bank employee, they have only access to a local area network. And from that local area network, the connection is established to a wide area network. No end user, no terminal actually connects to the wide area network directly. You always connect through your local area network first. So that's one example. This is how we remember that basically wide area networks are a network of networks, and your banking example is one good idea. It should give you a good idea of how that wide area network is created. Okay, so but the internet is the largest wide area network. It has a global approach. And the interesting part is that you always access internet as a single identity. So you never have to say that I didn't find this particular website on this internet. I will look on that internet, and if I'll not find it on that internet, I will find it on this internet and that internet, and I'll want it at fifth or sixth internet. No, you don't do that. You access internet as a single entity. For you, it's just that single big network known as the internet. And when you want to access a particular server, that entire network connects you to that server eventually. But for you, the internet is just one single entity. That's it. One entire network. And it's amazing to think about it. It is such a huge network. It's such a huge network. And everything is just a click away from you, a button click, a tap, a HTTPS, hyperlink away for you. That's it. It's connecting, hyperlinking your way through different web pages with a click of a button. That's it. And that's how easy it is to browse or surf through this entire huge network. So what we know about the internet is that it is the largest wide area network, no doubt, and it's actually scattered all over the planet, but we access it as a single entity. Just it's just only one network, and we can connect to it as long as we have an active internet connection. And currently it's still evolving. So as far as we know, that there are new servers being set up, new websites being set up, new networks being set up. So it's still an evolving entity. And most importantly, there is really no one authority who owns the internet. There's no one. There's no hierarchy of the internet whatsoever. There's no governing body who claims that I own the internet. No, not like that. Basically, internet is this huge, gigantic network. It's this gigantic monster that has no such architecture, no hierarchy whatsoever. It's just growing into this massive thing it is. But there are hierarchies in the sense of internet service providers. We'll be looking into that in the next lectures. But right now, just revise through, just to summarize what we've done so far, is that we discussed most details, a lot of details about local area networks. And now we're going to be switching gears and focusing our attention towards the internet and its services that it provides to our end users and how it's organized. And the architecture that we're mentioning, there is no architecture, but the single architecture or the single hierarchy that we see with respect to internet, that is the internet service providers. And we'll be looking at that in the following lectures.